Welcome back, everybody. We'll take a look at a few more examples of optimization problems. These will be a little more involved than the ones we saw in the previous video, okay? So first up, find the point or points on the curve y equals x squared plus 1 that are nearest the point 0, 4. Okay, so this is x squared plus 1 is what that syntax means, okay? And we want to find the point on this parabola that's nearest the point 0, 4. So I'm going to start with a sketch. And x squared plus 1, a parabola shifted up 1 unit. And then 0, 4 will be right here. So there's that point. Okay? And the idea is we want to find the single point or the pair of points on the blue curve that are nearest the point 0, 4. And you know, this is symmetric about the y-axis, so if this is the point that's nearest, there's going to be a corresponding point over there, okay? So there might be two corresponding points, but look, here's how we're going to work this, okay? I am looking for the point on this curve. We're going to call it an arbitrary point xy. If we want these 2 points to be as close as possible, think about what it is we're minimizing here. We're minimizing the distance. So I'm going to label this D. Okay, so our job is to find the point xy that minimizes the distance between the parabola and that other point, 0, 4. Okay, so please recall your distance formula from geometry. Okay, distance is the square root of x2 minus x1 squared plus quantity y2 minus y1 squared. Okay, so there's your old school distance formula, and basically you're plugging in a pair of coordinates here, okay? And that's what we have. We've got this arbitrary point xy, we've got this other point 0, 4. So I'm going to think of these as like my x2 and my y2, and I'm going to let these be my x1 and my y1. So our optimization equation becomes distance equals radical. Okay, x2 minus x1 is going to look like x minus 0 here. x2 minus x1 quantity squared plus y2, which is y, minus y1, which is 4 quantity squared. And this is what we're looking to minimize. Now, as usual, we have variables on both sides of the equation, and we have 2 variables inside the right-hand side of the equation. We're going to want to clean this up in a moment. I will do this real quick. X minus 0 is just x, so I can make that look a little nicer like that, okay? In terms of the constraint equation, okay, look, we're actually given the constraint equation. We are looking for this point, x comma y, and what do we know about that point? It has to lie on this parabola. So the equation of the parabola itself is our constraint, y equals x squared plus 1. We're not going to get back the point 1, 1 because that doesn't lie on the parabola. Okay, we got to get back points that lie on the parabola. So the constraint is just the equation of the parabola itself. Okay. And what's nice about this is that you notice it's already got the letter y by itself. So we can go ahead and sub that in. So I'm going to replace y with x squared plus 1. And I'll clean that quantity up a little bit. And we're getting radical x squared plus x squared minus 3 quantity squared when I clean up inside the parentheses, okay? And so there is our distance formula, all right? And now it's in terms of a single variable x, and we can actually go ahead and take the derivative of this. So I'll call it d prime, and if you think about it, we are going to have to use the chain rule here, okay? It's this whole quantity raised to the 1/2 power, so I'm going to write it that way. It's this whole thing to the 1/2 power, okay? So applying the chain rule, I'll start with this. And we're going to get 1/2, leave the inner quantity alone. Now the negative 1/2 power. Now we multiply by the derivative of the inside. So that's going to be 2x, and now another little chain right here, okay? 2, leave the quantity alone to the first, derivative of the inside is another 2x. And it looks ugly and it looks gross, but, you know, we've got our calculators to help us out here. And what's nice is this. Look, we're looking where the derivative equals 0. Notice the type of exponent this first term has. It's got a negative exponent. That whole thing is going to be in the denominator, okay? And this is the stuff that's basically left up in the numerator, okay? If you want to take a moment to rewrite this as a single fraction, be my guest. But look, when does a fraction, remember this is going to be in the denominator. This is going to be in the numerator, okay? When does a fraction equal 0? When the numerator equals 0. So even though the derivative came back kind of ugly and tedious, we really just need to focus on this portion of it, okay? If you want to graph the whole thing in your calculator, you can do that, okay? But this is where I'm really, in this lesson, going to be using the graph of the first derivative to get the appropriate critical points, okay? So look, you can either just graph this, you can graph the whole thing. If you graph, I think, the whole thing, you end up getting back something like this, okay? Here's the graph of the first derivative. I'll do it in purple. Looks something like this, okay? And now, if this is the derivative, these are our critical points where it's crossing the x-axis. So you might have on your calculator y1 equals this derivative equation, okay? Put y2 equals 0 in. Hit enter. That's going to graph the x-axis. You're not really going to see anything because it's just the x-axis. But now what we can do is find these intersection points, okay? And to do that, make sure your calculators are on, and you're going to go to, let's see, second calc at the top of your screen. And you're going to pick up number 5, intersect. Okay, and it's going to ask you first curve, second curve, and then enter. So the first curve, you just want to make sure, basically the idea is this. Get your cursor near one of the intersection points. So you might have to hit left or right to move the cursor around, but you want to get the cursor near these intersection points, okay? And if you do that and then hit enter 3 times, it's going to give you these intersection values. So here we get about 1.581. And in this class, when we use the calculator, we round to 3 decimal places. Here we get x equals 0, and here we get x equals negative 1.581. Okay? Now I can look at this graph of d prime, and I see right away that we actually have 2 minimums and 1 max. How do I know that? I look at the sign changes. From here, we go negative to positive. So this is going to be a relative min. At 0, notice we're going from positive to negative. This is actually a relative max at 0. And then at 158, we're changing the derivative from negative to positive. We've got ourselves a relative min again. So it looks like the mins come in pairs of x values. X is going to be positive or negative 1.581. And when that's the case, we minimize the distance to the point 0, 4. Okay, so if I relabel this, this is like 1.581 something. Over here on the other side, we would have negative 1.581 something. And to get the y value that goes with it, go back to your constraint and plug in that x value of 1.581. Okay, and when you punch that in, you get about 3.5 back for y. And so those are the 2 points, the pair of points that are closest to the point 0,4 that lie in the parabola. Now, something interesting of note here was notice that we got a relative max at 0. That would be this point right here. 0, 1 is actually a relative max distance to the point 0,4. So think about what's going on here, okay? As we're coming down this parabola, okay, we're actually getting closer and closer to the point 0,4 until we get to that point. Now we're as close to 0,4 as we're going to get. Now I'm actually getting a little further away from 0,4 when I get here. Now I'm getting a little closer again, so there's our relative min, and now I'm getting further away. In this little area, this is actually a relative max distance, okay? But again, you know, the big deals here was knowing how to set up the distance formula, all right? And then understanding that the equation of the parabola is its constraint, and then we go from there. In terms of the derivative thing, if you're doing it algebraically, you would set just the numerator equal to 0 with the help of the calculator. It's not too bad punching the whole thing in and then analyzing the graph of the first derivative for max mins. Okay? Let me know if you have questions on that. Moving into the next one. What is the largest rectangle that can be inscribed in a circle of radius 4? All right, we've got a circle of radius 4. There's a lot of ways I can inscribe a rectangle. That just means the corners of the rectangle are on the circle. So if I make it real skinny like this, probably not going to have too much area. Whereas if I do something like this, I would imagine this rectangle is going to have considerably more area than the pink one. Okay? So in any event, what is the largest rectangle we can inscribe in a circle of radius 4? Okay, so here's what I'm going to do, right? Because we want variables and stuff. What I'm going to do is I'm actually going to graph this circle on the axes, and to make life as easy as possible, where do you suppose we're going to center this thing? Right at the origin, okay? So here we have our circle of radius 4. And what would the equation of that be? X squared plus y squared equals not 4, but 4 squared, which is 16. This is our constraint, okay? That we know we're bound to that. Now, here's the deal. Look, we've got this rectangle that we're trying to maximize inside of this circle. So I'm going to draw the rectangle. Okay. And we want the maximum possible area. We know area is going to be base times height. We need a way to represent that, okay? Here's the idea. One of the big reasons I center this at the origin is because it's symmetric. To the left and right it's symmetric, and up and down it's symmetric. Here's what I'm going to do. I'm going to call this distance right here, from here to the right, okay, x. Okay? Whatever x is, basically here's the deal. I'm looking for this coordinate. Let's call this coordinate xy. What is the coordinate xy that's going to maximize the area of this rectangle? Okay, so I'm going to call this coordinate up here xy, and I'm just choosing the first quadrant up there because it's the most convenient quadrant to work in. You can work in any. But think about it. If this is the point xy, it means that from here we went to the right x steps, right? And so that's why I have an x labeled on the bottom of this rectangle. But think about the symmetry. If I go back to the left, that's also going to be a length of x steps. What does that make the entire length of the bottom of this rectangle in terms of x? 2x from left to right. Considering I gave this a coordinate I'm calling y, that means that I went up y units from the origin. So that means this distance is a length of y. Well, again, because of the symmetry, that would also be a length of y. What does that make the entire height of this rectangle? 2y. Okay? So again, we put a coordinate up here. We called it xy. That told us then that the base of this rectangle will be given by 2x, and the height of the rectangle will be given by 2y. We are looking to maximize the area of this thing. Largest possible rectangle. Maximize the area. Area equals base times height. In this case, area equals 4xy. And again, the constraint is just the equation of the circle because the point we're looking for has to lie on that circle. Okay? And so again, you know, the tough part to me is done. Now we go through the process. Let's get something by itself up in the constraint. I guess I'll solve for y. Doesn't much matter here. And when we take the square root, it's the square root of this entire difference. It doesn't become 4 minus x, nothing like that, okay? It's not the square root of the individual terms. It's the square root of the entire difference, okay? And again, for convenience, I'm going to use the plus when I sub in. So subbing in to our optimization, I'll replace y with the positive version of the square root. Area equals 4x times y, which is now radical 16 minus x squared. Okay, and again, we're looking at, looks like product and chain to get through this derivative, so I'm going to rewrite that as the 1/2 power. Okay, but we do have product and chain here. So taking the derivative, a prime, derivative of the first term is just 4 times the second. Keep the first term, now the chain rule. Bring down the half, leave the inside alone. Derivative of the inside, negative 2x. Okay? So there's our derivative. If you want to clean it up a little bit, you can. I know the 2 and the 1/2 will cancel. A prime is 4 radical 16 minus x squared because of the 1/2 power. And then just be careful. It looks like this. Let me choose a better color to highlight. 4x times negative x is negative 4x squared in the numerator. Oh, and I missed my power here, right? When I dropped the 1/2 down front, I got to remember to subtract 1. So we have that negative exponent, okay? So again, take a moment to go through the derivative if you need to, okay? But just realize now we're going to have a minus 4x squared over the square root of 16 minus x squared for the second term. Certainly not something I want to set equal to 0 and solve. So again, I am going to graph this in y1, and I'm going to graph y2 equals 0 and look for the intersection points, okay? And so here's what I get when I graph a prime on my calculator. More or less kind of looks like this. It's like going up, and then I lose sight of it, and then it comes back down. Okay, so here's the graph of a prime. I am looking for a relative max. I want the largest possible rectangle, so I want a prime to change from positive to negative for a max. Okay, a max, a prime changes positive to negative, and that occurs right there. So again, if I use my intersect function on the calculator, I am getting that x is about 2.828. Okay, that's the x value I'm getting. All right. And now, once we have that, we verified it's a max because the derivative changed from positive to negative. We can try to answer the question, what is the largest rectangle? So ultimately, we want the area of the largest possible rectangle. So think about it. I can come back up to my original area formula. Now that I have x, I can get y. I can sub it into this. Or again, keep in mind we do have an area formula just in terms of x. So if I just use that with the x value I found, we should have our max. So a max is going to be 4 times this x value times 16 minus that x value squared to the 1/2 power. Okay? And if you punch that in, you're actually going to end up with 32 on the nose. Okay? 32 square units on the nose is what it'll round to 3 places. Okay? So if we have a circle of radius 4, the largest possible rectangle in there that can fit is a rectangle of area 32 square units. Okay? All right. Next up, a little different here. You'll see why. We will create an open top box. That's a box with no top from a rectangular sheet of 10 that's 9 by 12 inches. And by cutting by cutting corners of side length x inches from the corner. Let's just say by cutting squares. Okay, we're cutting squares of side length x inches from the corners and folding up the sides. Okay, so this is how we're going to make a box. Basically, here's the idea. We've got this rectangular sheet of tin. I'm going to cut out squares. And if you actually want to grab a piece of paper and kind of see what's going on here, you can do that. But if you cut out these squares, they're no longer there, and we've got these little tabs now that we can fold the sides up. Okay? So I'm going to do like a before and after diagram here. All right, so here's the before. We've got this rectangular sheet of tin that's 9 inches by 12 inches, and we're cutting squares of side length x inches from the corners, and then we'll fold up these tabs, these sides. So here's the before, here's the after, okay? Try and draw this like 3-dimensionally here, just do your best. And after we fold up the sides, it's going to look something like that. Okay? And so now our job is to kind of try to label this thing in terms of its side lengths, okay? What does x need to be? How far in are we cutting to maximize the volume of the box, okay? So we want to maximize volume. Now typically we think of volume of a box as length times width times height, okay? ultimately, these are all going to be in terms of x. So think for a moment about, let's call this the length, this right here, which came from this side. Now, originally, this was 9 inches long. But think about what we're doing. We're cutting in x inches, and we're folding up the sides. So like now, here's like basically the new dimension. When we fold up the sides, here's now the new base right there. So the question is, what is that length from here to here after I fold up the sides? Well, think about it. It was originally 9 inches long, and I'm folding in x inches on that side, and I'm folding in x inches on that side. Basically, I have 9 inches, and I'm losing 2x inches from both sides when I fold up the sides. Okay, and again, you might need to think about that a little bit. And then similarly, a very similar thing is going to happen when we find the width. I'll call this the width going back, okay? So originally that was 12 inches long, but again, I'm folding in an x number of inches from both sides. I'm losing x inches from both sides. This becomes 12 minus 2x inches. And think about the height of this thing. That's just the size of the tab itself. What's that? X inches. Okay? And so here, we don't really need a separate constraint equation. Once we have labeled this, we now have everything in terms of x. We don't really need a separate constraint equation. I just need to replace all these guys with what they're equal to in terms of x. So the length we said was 9 minus 2x, the width 12 minus 2x, and the height itself x. Now we've got volume all in terms of x. If you want to do a double product rule because you like doing things the hard way, you can do that. I'm going to completely get around the product rule. First, I will multiply out this. And we're looking at 108. Minus 18 minus 24 is minus 42x plus 4x squared. And then we've got that last x to distribute through. And there's velocity with probably as nice as it's going to look, okay? And so now if we take the derivative of this, we're going to get 108 minus 84x plus 12x squared. And it's just a parabola. You can set it equal to 0 and solve by hand if you'd like. But again, I am going to graph this on my calculator. And when I graph this parabola on the calculator, it looks something like this. Okay? We want max possible volume. We're looking where V prime changes from positive to negative then. That's right there. Okay? So again, if I find the intersection point here, we should get that x is about 1.697. Okay? So again, graph 0 and y2, and then do a calc intersect on your calculator to get that value. Okay, and that's all we wanted was what does x need to be to maximize the volume? Well, if we can measure in 1.697 inches on the nose, we will maximize the volume of this box. We will be able to hold as much stuff as possible in there. Okay, and one last example to go. Here it is, a closed box. This box has a top on it with a square base. Is to be built from materials that cost $10 per square inch for the bottom and 10 cents, excuse me, per square inch per bottom and 5 cents per square inch for the sides and the top. If the box must have a volume of 36 cubic inches, what is the minimum cost of production? What's the minimum it's going to cost us to have a box with a square base that costs 10 cents per square inch for the bottom and 5 cents per square inch for the sides and top? Maybe the bottom's made of a more rugged material. Maybe that's why it costs more. Who cares? Okay, whatever. But let's see if we can figure this out, okay? Because this is a doozy. So look, we've got this box. I'm going to draw that kind of three-dimensionally. So I draw a rectangle. I draw a congruent rectangle kind of overlapping it. And then I connect the corners here, okay? So there's our box, okay? Now again, we can typically go length, width, height. But as I read through, a box with a square base, so I know that these two dimensions are going to be the same. Call them both L, call them both W, call them both whatever you want. I'll go L, I guess, here, okay? And I'll call this H for height. So there's our box with a square base, labeled in terms of length and height. Okay, Now we're talking about all these costs, and then we're told the box must have a volume of 36 cubic inches. There's our constraint. Okay, it has to have a volume of 36 cubic inches. Well, how do we get the volume? Length times width times height, which in this case is going to be length times height. So in other words, L squared times H is going to equal 36 here. So there's our constraint, set equal to a constant. Now the optimization, this is a little more involved, okay? We want to minimize the cost. So we need an equation representing the cost of this thing. I'm going to use the letter C for cost. Cost equals. Well, what is cost based on? Well, it's based on the side we're working on, and notice that we're talking about square inches. If we're talking square units, what are we talking about? We're talking about the area of those sides, okay? So the bottom of the box is 10 cents per square inch. So whatever the area of the bottom is, I got to multiply that by 10 cents per square inch, and I will get the cost. For example, if this is just 2 square inches, and it's 10 cents per square inch, what's it going to cost? Hopefully you're thinking, oh, 20 cents. 10 cents for the first square inch, 10 cents for the second. How did we do that? We multiplied its area, 2 square inches, by its cost. In a more general term, what is the area of this given by? L squared. So it's the area times the cost per square foot. So this is the cost of the bottom. The top and sides cost a little less, 5 cents per square inch. So let's talk about the top. The area of the top is going to be L times L squared. But oh geez, I am being sloppy here. Okay, that should be 0.10. 10 cents a square inch for the bottom. Jeez. 10 cents per square inch for the bottom. That's that bottom. Top is 5 cents per square inch for the top. So the area is L squared. The cost is 0.05, okay? Then we've got the sides. Now, all the sides are the same cost, 5 cents per square inch. Let's look at the areas of the sides. Think about the front. What's the area of this front going to be? L times H, okay? What's the area of the back going to be? Well, it looks like another L times H. So there's 2 sides of area LH. What's the area of this side going to be? Oh, it looks like L times H. There's 3 sides of area LH, and the last side also has dimensions L times H. What does that mean? It means we have 4 sides. So it was front, back, left, and right sides, all of the same area, LH, times the cost of 5 cents per square inch. And there now is our cost equation. Area bottom times the cost per square foot of the bottom, square inch of the bottom. Area of the top times cost per square inch of the top. Area of the remaining sides times 4 times the cost per square inch of the sides. Okay, and so obviously the most involved of our optimization formulas thus far, but there you go. Let's clean this up. We've got some like terms. We've got 0.1 L squared plus 0.05 L squared, 0.15 L squared, and then plus 0.2 LH. There's our cost equation. And again, the tough part is done. Now we go through the process. Let's solve this for H, because then we don't have to take any square roots, and I'll replace H in my equation with 36 over L squared. So here goes. Cost is 0.15 L squared plus 0.2 L times 36 over L squared. And let's clean that up. Let's see, 0.2 times 36 is 7.2. And L over L squared is L to the negative first power, or 7.2 over L. Okay, but I'm going to leave it with that power so that I can take the derivative pretty easily. So now we're ready to derive. dc over dl if you want, or just c prime is fine with me. 0.3 L to the first minus 7.2L to the negative second. There ends up being the first derivative of cost. Looking at the graph of C prime, again, graph that in Y1, just use the letter X on your calculator. Graph Y2 equals 0 to find the intersection point. When you graph it, it should look something like this. Kind of shoots down like that and then comes back up from the side. There's the graph of C prime. We are looking to minimize the cost. We want to see where C prime changes negative to positive. It's precisely what's going on right there, below to above. So again, pick up that intersection point. We're calling it L, and I'm getting about 2.884. When L is 2.884, the length of the bottom of the box is 2.884. We will minimize the cost of producing this box. And so now I actually want the minimum cost of production. Once again, as a reminder, I can come up here and solve for H now that I have L. I can go back and plug it into this original cost equation in terms of L and H. But more simply, remember, we do have this just in terms of L. And so that's what I'm going to use to get the minimum cost. So C min occurs when L is 2.84. So we're looking at 0.15, 2884 squared plus 7.2 times that value to the negative first. And I am getting a minimum cost of about $3.74 when I round to the nearest cent. Money is the exception to the rounding rule. Round to 3 places always, unless you're talking about money. Now, nearest cent's good. If you're talking about living things, nearest whole number is good. Okay, but don't worry too much about the rounding conventions. If you always go 3 places, I'll never mark you wrong. All right, folks, but there you go. There's a lot of optimization. Take some time to digest it. Some problems, obviously, a little easier than others, but really a great application of calculus, okay? Reach out if you need help, and have a